Picture 400 generations born and dying inside a metal tube. No one aboard will ever see Earth. No one will live to see the destination. That's what a generation ship is, a self-contained world drifting between stars for 10,000 years, carrying humanity's last hope to a planet we can only guess is habitable. The engineering challenges are staggering. The life support must recycle every molecule. The hull must withstand micrometeorite impacts for millennia. But here's what the dreamers never talk about. Every single system keeping those people alive will fail. Not once, dozens of times. Across centuries where no replacement parts exist and no rescue mission is coming. The radiation shielding will degrade, the water recyclers will clog, the genetic database will corrupt, and the first thing that starts breaking down isn't the machines, it's something far harder to fix. The voyage scale. The nearest potentially habitable exoplanet is Proxima Centauri b, 4.24 light-years away. At 0.01 c, which is 1% light speed and the upper edge of what chemical or early fusion drives might achieve, that's a 424-year voyage. But realistic estimates put generation ships closer to 0.001 c, meaning the journey would stretch to 4,240 years. For a true deep space target like TRAPPIST-1e, 40 light-years out, you're looking at 10,000 to 40,000 years depending on propulsion. We can't go faster without technologies that don't exist. Antimatter engines, Bussard ramjets, breakthrough physics. Current ion drives top out around 90 kilometers per second. Voyager 1, our fastest object, moves at 17 kilometers per second, which is 0.006% light speed. So you're not building a ship, you're building a civilization in a can, adrift for 400 generations with no ground beneath their feet and no sky above, which means the ship that launches will look nothing like the ship that arrives. The crew problem. To survive 400 generations without genetic collapse, you need a minimum viable population. The consensus among geneticists sits between 500 and 1,000 people, providing enough diversity to avoid inbreeding depression, genetic drift, and the accumulation of harmful mutations. Below that threshold, you hit the founder effect. Recessive diseases surface, fertility drops, immune systems weaken. Island populations on Earth show this pattern clearly. The Pitcairn Islanders, descended from 9 bounty mutineers, suffered severe genetic bottlenecks within 6 generations. A crew of 500 means social structure becomes non-negotiable. You need doctors, engineers, farmers, teachers, all cross-trained because specialization is a luxury. You need conflict resolution systems, governance that endures regime changes, and a culture that doesn't fracture into factions. Every person matters. Every birth is monitored. Every pairing is, to some degree, managed. Keeping those genetics stable turns out to be the easy part. The first generation. The volunteers who board that ship know the terms. They'll live their entire lives inside those walls, have children who'll do the same, and die without ever seeing the destination. Their children will die in transit, so will their grandchildren, and 395 generations after that. The psychological screening for that first crew is unprecedented. You're not just selecting astronauts, you're selecting the ancestors of a civilization that won't exist for 10,000 years. They need to be stable enough to thrive in confinement, but adaptable enough to raise children who'll never know Earth. Some mission models suggest selecting younger crew members, maximizing their reproductive years aboard. Others argue for older volunteers who've already lived full lives on Earth. Either way, you're asking human beings to accept that their lineage will spend 400 generations in a metal tube hurtling through the void. The ethical weight is staggering. Those first children didn't choose this. Neither did the 10 millionth person born aboard halfway through the voyage. What they don't know is that their great-great-grandchildren will face a crisis the mission planners never predicted. Language drift. Language mutates, fast. Linguists estimate that after 400 generations, roughly 10,000 years, the crew arriving at the destination would speak a language completely unintelligible to the crew that launched. That's the span from ancient Sumer to today. Old English texts from 1,000 years ago are already unreadable without training. Go back 2,000 years, and Latin has fractured into a dozen Romance languages. At 10,000 years, you're looking at linguistic drift so extreme that the original mission logs, the technical manuals, even the cultural records might as well be alien artifacts. Some designs propose a formal, conserved language taught alongside the evolving vernacular, the way Latin persisted in medieval Europe. But that requires deliberate effort every single generation. One lapse, one cultural shift, one generation that decides the old tongue doesn't matter anymore, and the link breaks. The crew 300 generations in might speak a hybrid Creole, blending a dozen intermediate forms. They might still call the ship by its original name, but the word means something different now. And if they can't read the original manuals, the technical knowledge starts dying too. The knowledge problem. Knowledge doesn't survive by default. Every child born aboard has to be taught engineering, medicine, agriculture, navigation from scratch. That's 10,000 years of unbroken teaching, generation after generation, with no outside universities, no internet, no way to look something up if the last person who knew it dies. Anthropologists call this the fragility of oral and early written cultures. A single plague, a single conflict that disrupts schooling for a generation, and critical skills vanish permanently. How do you restart a fusion reactor if the last engineer died before training a successor? How do you treat a new disease if the medical texts are in a language nobody reads anymore? Some missions propose radical redundancy, multiple independent schools, recorded video libraries, apprenticeship requirements, but institutional knowledge is different from recorded knowledge. You can read a manual on heart surgery without ever being able to perform one. The crew needs hands-on expertise, renewed every 25 years, for 400 cycles. And children resist. They push back against the old ways, reinterpret the texts, simplify what seems unnecessarily complex. Over centuries, that erosion compounds, which is why every generation ship design includes something controversial: artificial intelligence that never forgets. The AI question. The ship's core AI isn't conscious. It doesn't want anything. It's a librarian that never sleeps, a technician that can't misremember a procedure, a teacher that holds every schematic, every formula, every repair manual exactly as it was written on Earth. Generation 1 programs it. Generation 200 inherits it. It monitors life support, catches system degradation before humans notice, and flags genetic drift in the agricultural stock. It teaches navigation to teenagers who've never seen a star move. It answers questions about Earth that no living person can. And it never interprets, never adapts, never evolves. That's the design. But after 200 generations, who's actually in control? The crew executes what the AI recommends because it's always been right. They defer to its botanical protocols, its maintenance schedules, its resource allocations. Functionally, they're following orders from a machine their ancestors built. Some mission planners argue the AI should have override authority in emergencies. Others say that's how you get a crew that stops thinking for itself, that can't improvise when the unexpected happens 8 light-years from home. There's no good answer. Both paths end somewhere uncomfortable. But there's a more immediate threat than AI rebellion. Radiation shielding. Outside the ship's hull, interstellar space is saturated with cosmic rays. High-energy protons, heavy nuclei, particles accelerated to near light speed by supernovae and colliding galaxies. Earth's magnetosphere deflects most of them. The ship has no magnetosphere. A single cosmic ray can punch through a human cell and shatter DNA in multiple places. Cumulative exposure means cancer, cataracts, central nervous system damage. The mission lifespan is 300 generations. Acceptable radiation dose over that span is effectively zero. So you layer the hull. 5 meters of water, the best neutron absorber. Polyethylene panels for hydrogen-rich shielding. Some designs propose active magnetic fields, bending charged particles around the habitat module. Every kilogram of shielding is propellant you didn't bring, deceleration margin you don't have. The best current models can reduce exposure by 80%, maybe 90%. That still leaves a baseline flux 50 times higher than Earth's surface. Elevated cancer rates are baked into the mission profile. The medical bay will see leukemia cases in children, gliomas in young adults, over and over, for 10,000 years. Even with perfect shielding, there's one type of radiation the ship can't block. Muon flux. When a cosmic ray slams into your shielding, it doesn't just stop, it shatters into secondary particles, muons. They're born from the collision, traveling at 0.99 C, and they don't care what's in their way. They pass through lead, through water, through human tissue like it isn't there. A muon crossing a cell leaves ionization damage along its track. One muon, one microscopic scar in the DNA. But the ship is flying through a muon flux generated by its own shielding, 24 hours a day, 10,000 years. Every person aboard takes hits constantly. The damage accumulates across a lifetime, across generations. Studies on Earth estimate muon exposure at sea level contributes about 0.3 millisieverts per year. Inside the ship, even with maximum shielding, crew exposure could reach 50 to 100 millisieverts annually. Childhood cancers triple. Heritable mutations appear in the third generation. By generation 50, the oncology ward never closes. There's no way to stop it. You can't shield against muons without making the problem worse, generating more secondaries. The mission accepts this cost. Every child born is born into a radiation field their genome wasn't designed for. They'll live shorter lives, lose more peers, bury more of their own children. It's written into the physics, which is why the ship's hospital will be its most essential facility and the first to face impossible choices. Medical triage. The ship carries 2 MRI machines, 4 surgical suites, and a pharmacy stocked for 50 years. After that, you're synthesizing everything on board. Antibiotics degrade. Anesthetics break down. The genetic diversity in a crew of 10,000 means organ matching becomes a lottery, with worse odds every generation. You can't manufacture replacement heart valves without rare earth elements you didn't bring enough of. You can't treat autoimmune disorders that require biologics grown from cell lines that won't survive 200 years of cryostorage. A teenager develops leukemia. The treatment exists, but uses the last viable batch of a drug 300 other people might need. So, the medical council meets. They decide, not based on who's sickest, but on who's most critical to the mission, who has the rarest skills, who carries the genes the population can't afford to lose. It's not triage, it's arithmetic, written in lives. And some of the diseases they'll face won't exist yet when the ship launches. Evolutionary pressure. Because natural selection doesn't stop just because you're in a spaceship. The environment is selecting. 0.3 G instead of 1 G favors longer, thinner bones. Recycled air with slightly elevated CO2 selects for more efficient respiratory systems. Cosmic radiation at 0.5 sieverts per year favors DNA repair mechanisms the rest of humanity will never develop. Over 400 generations, those aren't quirks, they're speciation events waiting to happen. The children born in year 9800 won't just look different. Their hemoglobin might bind oxygen at different partial pressures. Their circadian rhythms might drift from 24 hours because the ship's lighting never gave them a reason to stay synchronized with Earth's day. They'll be optimized for the ship, not for a planet with weather, with pathogens, with 1G pulling at a skeleton that's been light for 300 generations. You're engineering a population to survive the journey, and in doing so, you might be engineering them to fail at the destination. What nobody planned for is that the adaptation might make them incompatible with the destination planet. Gravity systems. The only way to create artificial gravity without magic is rotation. Spin a cylinder 500 meters in radius at 1.4 rpm and the rim experiences 1 g. Go faster and people vomit. Go slower and bone density collapses. The engineering isn't theoretical. O'Neill proved the math in 1974. But Coriolis force is real, and it's weird. Drop a ball and it curves. Walk spinward and you feel heavier. The inner ear of a child born rotating never learns to distinguish real acceleration from artifact. By generation 5, their brains are wired differently. Vertigo, on a non-rotating platform, becomes the norm. The structure has to hold that spin for 10,000 years. Every rivet, every weld, every structural beam is under constant centrifugal load. Metal fatigues. Microfractures accumulate. The hull is 8 centimeters thick steel and aluminum composite, and somewhere in year 4200, a crack propagates through a load-bearing ring. You can repair it, you can reinforce it, but rotation creates a problem that gets worse every single day the ship travels. Structural fatigue. Every rotation adds stress. The hull flexes, microscopic cracks appear in the welds, and over decades those cracks grow. After 1,000 years, the metal has endured 500 million complete rotations. On Earth, bridges are replaced every 50 to 100 years because of metal fatigue. This ship has no dry dock. Repair crews work in pressurized suits, welding from the inside while the structure spins around them at 2 revolutions per minute. A weld fails in one spoke, load transfers to the others, and now you're racing to reinforce 6 connection points before the geometry shifts enough to buckle the ring. Miss one, and the entire rotating section could shear away from the hull. The ship carries replacement panels, redundant struts, backup bearings, but you're betting the integrity of a structure larger than any building ever built on welds made by people who've never seen Earth, using tools that are themselves 3,000 years old. And if the rotation stops even briefly, everyone aboard faces a countdown to suffocation. The oxygen cycle. Humans need oxygen. 1,000 people consume roughly 800 kilograms of O2 every day. The ship can't carry 10,000 years of reserves, so it manufactures oxygen in a closed loop. Algae tanks and crop biomes photosynthesize CO2 back into breathable air. Backup systems run electrolysis, splitting water into hydrogen and oxygen. But water is also finite. CO2 scrubbers pull carbon from the air and feed it to the plants. The margin is tight. Lose 10% of your algae and atmospheric oxygen starts dropping within weeks. Here's the spiral. Oxygen falls, people get hypoxic, cognitive function declines, mistakes multiply, fewer hands to tend the biomes, more plants die, less oxygen. The cascade accelerates faster than any rescue can stop it. Redundancy helps. Isolated biome sectors buy time, but every backup pulls from the same water and nutrient reserves. You're not just keeping plants alive, you're keeping a biochemical cycle balanced to within 2% for 400 generations, which is why the ship's farms aren't just for food, they're the literal air everyone breathes. Agricultural systems. Feeding 1,000 people requires roughly 2,500 kilograms of food per day, or 9 million kilograms per year. The ship grows it all hydroponically: wheat, rice, soybeans, leafy greens, algae protein. No soil, just nutrient film flowing over roots under LED arrays tuned to photosynthetic peaks. Crop diversity is survival. A fungal blight wipes out your wheat. You still have 11 other staple crops. But pollination is a problem. Earth bees don't exist here, so you hand-pollinate or genetically engineer self-fertile varieties. Every calorie is accounted for. Every harvest is measured against projections made 200 years ago. Waste is cycled back. Human waste, dead plants, food scraps, all composted, broken down, nutrients extracted, and returned to the hydroponic solution. Nothing is thrown away because there's nowhere to throw it. The loop has to close perfectly or you slowly starve. And it works. As long as the LEDs stay lit, the pumps keep running, and the nutrient balance holds. For 10,000 years. But there's one resource the ship can never make more of, and it's running out from day one. Phosphorus limit. Phosphorus. Every strand of DNA wraps around a phosphate backbone. Every molecule of ATP that powers every cell in your body is built on phosphorus. Your bones are 50% calcium phosphate by weight. Plants can't grow without it. And unlike carbon, nitrogen, or water, you can't synthesize it. There's no chemical reaction that creates phosphorus atoms. The ship launches with a fixed inventory, locked inside the bodies of the crew, stored in waste tanks, embedded in the soil of the farms. That's it. That's all you get for 10,000 years. Lose a gram to a jammed recycler, a contaminated batch of compost, a sealed room you can't access, and it's gone. The biosphere shrinks by that much, permanently. One major failure in the waste recovery system, and you could lose 15% of your total phosphorus in a single generation. Which is why the death protocols aboard a generation ship would seem horrifying by Earth standards. The burial system. There are no burials, no coffins, no graves, no scattering of ashes into the void. Every atom of a human body is a strategic resource. The dead are placed in industrial composters within hours of death, broken down at 60 degrees Celsius over 4 to 6 weeks. Bones are separated and acid digested to extract calcium and phosphate. Soft tissue becomes nitrogen-rich compost. Trace metals are recovered and returned to inventory. What was your grandmother becomes 45 kilograms of soil amendments, 1.1 kilograms of phosphorus salts, and a data entry in the resource ledger. The system doesn't care about last rites or mourning periods. The composters run on a schedule. Some cultures adapt. They build rituals around the transfer, frame it as rejoining the cycle, returning to the garden. Others never accept it. They see desecration, erasure. And some families will resist, no matter the cost to everyone else. Social fracture points. 400 generations is longer than recorded human history. In that span, every belief system fractures. Religious groups split over interpretations of scripture written for a planet they've never seen. Political factions form around resource allocation. Who gets the better quarters? Whose children are prioritized for education slots? On Earth, dissatisfied groups migrate. They leave. They build a new community 200 kilometers away. On a generation ship, there is no away. You're locked in 12 interconnected modules with the people you hate, their children, and their children's children. Exit is death. The ship's population is maybe 10,000 people, small enough that every faction knows every other faction by name, large enough that coalitions can form, that majorities can outvote minorities on life and death resource decisions, that resentment compounds across decades until it becomes identity. History suggests these conflicts don't stay verbal for long. Mutiny scenarios. In 1789, the HMS Bounty mutinied 5 weeks after leaving Tahiti. The voyage had lasted less than a year. Biosphere 2, sealed for just 2 years, saw its crew split into warring factions who stopped speaking entirely. Antarctic winter-over teams, isolated for 9 months, have recorded physical violence, sabotage of equipment, and complete psychological breakdowns. A generation ship faces the same pressures, but stretched across centuries. A faction that feels cheated on water rations doesn't petition, they cut power to hydroponics. A religious splinter group doesn't leave, they barricade the biodome and declare it sovereign territory. A mutiny here doesn't mean seizing the helm, it means jamming airlocks open, corrupting navigation databases, or reprogramming the AI to recognize only one bloodline as crew. You can't call for help, you can't sail home, you can't abandon ship. Every conflict becomes existential because the ship is the only world that exists. Reconciliation isn't optional, it's structural, And when it fails, the hull itself becomes a weapon, which is why the ship's design includes something most people would call dystopian: mandatory surveillance. Governance models. Every proposed governance model breaks down somewhere between Generation 4 and Generation 10. Rotating councils sound fair until the rotation favors engineers over farmers for 30 years straight and the food supply collapses. AI-mediated democracy sounds neutral until someone realizes the AI was trained on Earth politics and keeps optimizing for growth in a closed system where growth means death. Some designs propose genetic castes, certain families bred for leadership, others for labor, frozen at birth into roles they can't escape. Others suggest pure meritocracy, where only those who can repair a fusion reactor get to vote. Both systems calcify, both produce resentment, and on a ship where everyone knows everyone, resentment doesn't fade, it compounds interest across lifetimes. The real problem isn't which system you choose, it's that after 200 years, no one remembers why the rules exist. The council that once allocated resources fairly now allocates them to itself. The AI that mediated disputes now obeys whoever last updated its ethics module. And there's no appeals court, no UN, no external authority to correct course. Power doesn't just corrupt, it becomes biology. But no governance system can stop the one threat that's invisible and already spreading. Genetic bottleneck. Launch with 1,000 people and you've already lost. The human genome carries roughly 1.5 lethal recessive alleles per person, hidden, waiting for 2 copies to meet. In a closed population that small, they will meet. By Generation 5, rare genetic disorders start appearing in clusters. By Generation 12, inbreeding coefficients cross thresholds seen only in endangered species on Earth. Genetic drift accelerates everything. Neutral mutations fix randomly. Beneficial alleles vanish by chance. Harmful alleles spread not because they help, but because the math of small populations doesn't care about fitness. Run the models forward 100 generations and you're not looking at humans anymore. You're looking at a founder population sculpted by dice rolls, where the genes that survive aren't the best ones, just the luckiest ones. The clock is ticking before conception. Even with perfect genetic screening, even with maximized diversity in the founding crew, the bottleneck tightens every generation. By year 3000, the gene pool resembles an island species on the edge of collapse. By year 5000, some family trees don't branch anymore, they loop. Unless the ship does something that crosses a line, most ethicists won't touch. Reproductive control. The central computer runs the algorithm every 5 years. It analyzes the entire genetic database, maps every bloodline, calculates compatibility scores. Then it assigns partners. You don't choose who you marry. You don't choose if you have children, or how many, or when. The mission requires 12 births per cycle in genetic cluster 7, so 12 couples are selected. Refusal means losing your ration priority for a year. There's a frozen vault with 10,000 sperm samples and 10,000 eggs from Earth, rotated into the population every 3 generations to inject old diversity back in. But even that runs out by year 3000. Some proposals go further. Mandatory genetic screening of every embryo, termination of pregnancies that increase inbreeding coefficients above 0.125, 1 child per person, no exceptions, ever. And even with perfect genetic management, there's a mutation creeping in that no one will see coming. Microbiome collapse. Your body contains 39 trillion bacteria. They outnumber your own cells. They digest your food, train your immune system, synthesize vitamins you can't make yourself. Earth has millions of microbial species. The ship launches with maybe 50,000 if it's lucky. Every surface, every breath, every meal on the ship pulls from the same closed microbial pool. After 200 years, the gut bacteria of every passenger starts to look identical. The soil microbes homogenize. The air flora narrows to 6 dominant species. Diversity collapses because there's no wild reservoir to pull from. On Earth, you pick up new microbes from dirt, animals, strangers on the subway. On the ship, you only ever touch the same 900 people and their descendants. When a system loses diversity, it loses resilience. A single pathogen that can exploit one weakness now has 10,000 genetically similar hosts with genetically similar microbiomes. No competition, no resistance, no variation to slow it down, which is why a common cold from generation 50 could become a plague by generation 200. Quarantine protocols. The ship is divided into 9 pressurized sections. Each one seals independently. 3 airlocks between every zone, each with its own sterilization chamber, UV lights, chemical wash, 20-minute decon cycle. If an outbreak starts in Section 4, the bulkheads slam shut. Everyone inside stays inside. The air system cuts over to internal scrubbers. The rest of the ship keeps breathing. The math is brutal but simple. Section 4 holds 140 people. The ship holds 1,200. Seal it, and 140 die. Don't seal it, and you risk losing everyone. The captain makes that call in under 90 seconds, because waiting means the infection spreads to Section 5. There's no vote, no trial, no debate. The doors lock, the vents close, and the people inside have maybe 11 hours of oxygen left. But sealing a section doesn't just kill the infected. It traps families, children, people who will suffocate knowing they were abandoned. Psychological isolation. Now imagine you're born into a world 110 meters wide. You will never see a horizon, never feel rain on your skin, never meet anyone beyond the same 1,000 faces you've known since childhood. Antarctic winter overcrews show depression rates 3 times baseline after 9 months of isolation. Submariners on 6-month deployments report anxiety disorders at 14% versus 7% in the general population, and those missions end. Generation ship passengers don't get to go home. The walls are always the same color. The air smells like recycled breath and hydroponic tomatoes. You know every corridor, every face, every conversation topic. There is no novelty, no discovery, no escape. Suicide becomes an engineering problem. A single death creates a labor gap, breaks a family unit, destabilizes the gene pool, and the ship can't afford to lose a single person to despair. There's no replacement population. Virtual reality. So the ship equips every cabin with a VR headset. You can walk through forests that never existed, swim in oceans no one has seen for 200 years, meet strangers in a simulated city of millions. It's pharmacology for the mind. But here's the problem. Why would you ever leave? Reality is a 3-meter bunk and a shift in the algae farms. Virtual reality is a beach house in Bali, a hike through Patagonia, a night market in Bangkok. Which world feels more real after 30 years? Studies of VR addiction show usage escalation in confined environments. 2 hours a day becomes 8, then 16. You start sleeping in the headset. Your real-world relationships atrophy because your virtual friends are more interesting, more varied, always available. Eventually, a generation is born that spends 22 hours a day in simulation. They eat, sleep, and work the minimum to survive, then return to the only world that feels like living. Which raises the question, if they never experience the real destination, does it matter if they arrive? Purpose erosion. The first generation remembers Earth. They touched soil, breathed unfiltered air, chose this mission. Generation 2 knows Earth through childhood memories and photographs. Generation 200 knows it as a story their great-great-grandparents told, like we know the Trojan War. The destination planet, 300 generations away, becomes mythology, a place in a story. No one alive has seen it, will see it, or knows anyone who will see it. Sacrificing comfort today for a world 8,000 years away starts to feel absurd. Why ration water when abundance is one policy change away? Why enforce reproduction quotas when the planet is 47 light-years distant? Why maintain the fusion engines when you could convert that energy to better food, bigger living quarters, longer lifespans right now. The ship's constitution says the mission is sacred, but constitutions are written by the dead, and the living have to sleep in 3-meter bunks. Generational purpose erodes like a coastline, slowly, then all at once, and some generations will inevitably ask, why not just turn the ship around? The return faction. The faction starts small, a philosophy club, a grievance committee. Then it's 200 people signing a petition arguing they never chose this voyage, that their ancestors made a decision binding generations who had no vote. They want the ship to turn around. It doesn't matter that Earth will be 10,000 years older. It doesn't matter that everyone they descended from is dust. The argument is consent. You can't conscript the unborn into a one-way trip across the galaxy. The ship splits. Engineering refuses to consider it. The council calls it sedition. Families fracture along the divide. Some propose a vote, others a lottery, to decide who goes on and who gets cryoslept until return. Violence breaks out in Habitat C when someone tries to manually override navigation. The return faction grows because the alternative is admitting you'll die in a tube for a world you'll never see. But there's a physical reason turning around is impossible, even if everyone agreed. Velocity problem. To reach 0.01 c, 1% the speed of light, the ship burns fuel for 40 years. Constant acceleration. The rocket equation is merciless. Every kilogram of payload requires exponentially more fuel. By the time you hit cruising speed, 60% of your launch mass is gone. Deceleration at the destination requires the same fuel budget. You have to carry enough to slow down 10,000 years from now. That's already half your total fuel load spoken for before you even consider a return trip. A turnaround means you burn to stop, then burn again to accelerate back, then burn a third time to decelerate at Earth. You'd need 3 times the fuel you launched with. The ship doesn't have it. No generation ship design does. The math was locked in before the first passenger boarded. You can vote, you can mutiny, you can rewrite the Constitution, but you can't rewrite physics, which means the ship is committed from the moment it reaches cruising speed. There's no going back, only forward, or drifting dead. Fuel systems. Fusion engines burn deuterium and tritium, fusing hydrogen into helium and harvesting the energy release. The problem is sustained ignition. Tokamak reactors on Earth run for seconds. A generation ship needs 10,000 years of continuous burn with no resupply and no repair failures. Antimatter offers more energy per kilogram, but containment is the nightmare. Magnetic bottles hold antiprotons away from normal matter. A single containment failure, and the fuel annihilates itself in a gamma-ray flash. Over millennia, the odds of 0 failures approach 0. Bussard ramjets theoretically scoop interstellar hydrogen as they fly, fusing it into thrust. No fuel tanks. But the interstellar medium averages 1 atom per cubic centimeter. You need a magnetic scoop thousands of kilometers wide, and the drag from collection may exceed the thrust you gain. Every propulsion system has a single-point failure mode that kills the mission. Fusion requires parts that can't be replaced. Antimatter requires perfection across 300 generations. Ramjets require physics we haven't proven at scale. And if the engines die mid-voyage, the ship becomes a tomb coasting forever between stars. Navigation drift. So now the ship is sailing 10,000 years to Proxima Centauri, 4.24 light-years away. The problem is that when you aim at a star from Earth, you're not aiming at where it is. You're aiming at where it will be 10,000 years from now, accounting for its proper motion through the galaxy. A navigation error of just 0.01 degrees at launch translates to missing the target by 740 million kilometers at arrival. That's twice the distance from Earth to Jupiter. And errors accumulate. Stellar catalogs drift. Gravitational perturbations from rogue planets nudge the trajectory. Even the cosmic microwave background exerts a minuscule pressure over millennia. Course corrections are possible but expensive. A single 1 meter per second velocity change at the halfway point requires burning roughly 3% of the ship's remaining fuel, depending on mass. You get maybe 6 or 7 major corrections across the entire voyage before the margin vanishes. Miss a correction window and the error locks in permanently. Navigation relies on pulsars, those rotating neutron stars that tick like cosmic lighthouses with millisecond precision. But even pulsars glitch. Their spin rates change unpredictably, sometimes by microseconds per year. Over 5,000 years, those microseconds add up to positional uncertainties measured in billions of kilometers. But the ship isn't just drifting in space. It's drifting through time in a way that gets stranger the faster it moves. Time dilation. At 0.05 c, 5% the speed of light, time aboard the ship runs slower than time on Earth. Not by much. For every 10,000 years the crew experiences, Earth experiences roughly 10,012 years. A 12-year slippage sounds trivial until you remember this is cumulative and irreversible. The effect comes from special relativity. Moving clocks tick slower relative to stationary ones. At 0.1 c, the gap widens to 50 years. At 0.2 c, it's 200 years. If the ship could reach 0.9 c, which it can't, the crew would age 4,359 years, while Earth aged 10,000. 2 different timelines, forever desynchronized. This breaks every assumption about support from home. If Earth develops a breakthrough in fusion containment or medical nanotech in year 6000, the ship won't receive that data until year 6012 by Earth's calendar, but year 6005 by ship time. The crew is always living in Earth's past, while Earth is living in their future. Families on Earth will watch recordings of their ancestors aboard the ship, but those recordings are always delayed, always older than the people watching. A child born on the ship in year 5000 will be 12 years old before Earth even knows they exist, which means if Earth sends a message, the reply could arrive centuries after everyone who sent it has died. Communication lag. At 1 light-year from Earth, a distress signal takes 1 year to arrive. The response takes another year to return. 2-year round trip. By the time the ship is 2 light-years out, that's 4 years. At 5 light-years, 10 years. Every conversation becomes an exchange between generations. Emergencies become unsolvable. A reactor breach, a hull fracture, a pandemic. You're on your own. Earth can send advice, but by the time it arrives, the crisis has already resolved or killed everyone. At the midpoint, 5,000 years into the voyage, the ship is 2.12 light-years from Earth. A question sent home won't be answered for 4.24 years, assuming Earth responds immediately. Psychologically, this is corrosive. The crew knows Earth is still out there, still transmitting, but the lag makes every message feel archaeological. News arrives about wars that ended decades ago, leaders who've been dead for years, technological revolutions the ship can never access. Earth becomes a museum, not a home. And the lag only grows. By year 8000, round-trip communication takes 6.8 years. By year 9500, it takes 8 years. The transmission delay becomes longer than a human childhood. You send a message as a boy and receive the reply as a father. So the ship will eventually cross a threshold where they're too far to ever hear from Earth again, and they'll know the exact moment it happens. The silence point. Mission planners call it the silence point. It's not marked on any star chart, but every crew will cross it. The last signal from Earth arrives, is decoded, is read. Then weeks pass, then months. At first, they'll assume interference, solar flares, equipment drift, a temporary glitch in the relay network. They'll recalibrate the receivers, boost the gain, scan adjacent frequencies. But the static doesn't resolve into words. Historical parallels exist. In 1845, the Franklin expedition vanished into the Arctic. No word ever reached them that search parties had been dispatched, that their families were waiting, that the world still remembered. They died in silence, not knowing anyone was looking. The generation ship's crew will face the same uncertainty, but stretched across light years. Did Earth stop transmitting because civilization collapsed? Because they forgot? Or are the messages still being sent, degrading into noise across distances no radio wave was meant to cross? They'll never know which. And if Earth did keep sending, the messages would tell a story the ship's crew might not want to hear. Earth's evolution. Because 10,000 years is not a static interval. It's 400 generations of human cultural evolution, compressed into the time it takes the ship to coast between stars. The Earth they left will be unrecognizable. 10,000 years ago, humans were chipping flint in the Fertile Crescent. No writing, no cities, no metallurgy. The entire span from hunter-gatherers to smartphones fits inside the ship's flight time. Apply that rate of change forward. Earth's climate will shift through multiple oscillation cycles. Ice ages may come and go. Continents will drift centimeters. Coastlines will redraw themselves. The species composition of forests and oceans will turn over. And human civilization, if it survives, will rebuild itself dozens of times. Technologies the ship's crew couldn't imagine will be invented, refined, and abandoned. Propulsion systems that make their generation ship look like a wooden raft. Genetic engineering that renders baseline humanity obsolete. Artificial intelligence that solves problems the ship is still grinding through with slide rules and hope. Which means a faster ship might launch centuries later and overtake them mid-flight. The overtake scenario. The overtake scenario is a probability, not paranoia. If Earth develops antimatter drives in year 3000, a second expedition could launch at 0.3 C and arrive at the target star 4,000 years before the original ship. The colonists would find a thriving settlement, built by people who left 2,000 years after they did. In 2018, researchers at the University of Oxford modeled this exact problem. They found that for any realistic improvement curve in propulsion technology, launching early guarantees you'll be overtaken. The only scenarios where the first ship wins are those where technological progress flatlines or civilization collapses entirely. Now imagine the transmission. Generation 287, born in transit, never having seen Earth, receives a tight beam message. It's from humanity's third interstellar mission, launched 1,800 years after theirs, now decelerating into the target system. They'll be landing in 60 years. The message is friendly. It offers to wait. Every sacrifice, every birth, every death aboard that first ship is retroactively rendered meaningless. They were never the vanguard. They were the prototype, obsolete before they left the solar system, too slow to abort and too proud to admit it. And the psychological damage of that message could shatter the mission more effectively than any mechanical failure. Cultural drift. Because 400 generations doesn't just change the engineering, it changes the people. The ship becomes a world, and worlds grow their own cultures. The stories they tell won't be about Earth, they'll be about the crossing, the void years, the Great Seal failure of Generation 87. Their music will sound like metal harmonics and recycler hums, because that's the acoustic environment that shaped their ears. New religions emerge around the ship itself, around the mission, around the stars they'll never reach in their lifetimes. Taboos form around behaviors that threatened survival 200 generations ago. Ethics drift when your entire moral universe is 50,000 people in a tube with no outside reference. By the time they arrive, their art, their language, their values will be as alien to Earth as they are to the destination world. The mission brief said to preserve humanity, but what they'll deliver is something else entirely, which raises the question, are they even still human in the way we'd recognize? Speciation risk, because biology doesn't wait for mission control's approval. 400 generations is 10,000 years of selection pressure, and the ship is a radically new environment. Cosmic radiation damages DNA in ways Earth's magnetosphere never allowed. Low or variable gravity reshapes bone density, muscle attachment, cardiovascular response. The narrow genetic bottleneck and isolation means drift accelerates, mutations accumulate, and natural selection favors traits that work in a closed metal ecosystem. Shorter stature to conserve resources, higher radiation resistance, eyes adapted to artificial light spectra, immune systems that never encountered Earth's microbial diversity and can't recognize it. There's a threshold in evolutionary biology where two populations can no longer produce viable offspring. That's the definition of separate species. And 10,000 years in an alien environment might be enough to cross it. The mission was supposed to carry humanity to the stars. Instead, it might deliver humanity's successor. And if they've become a different species, the destination planet might reject them as invasive. Planetary compatibility. Because we chose the target world from 4.3 light-years away with 21st century instruments. Habitable meant liquid water and a rocky surface. It didn't mean safe. Gravity could be 1.4 g, enough to cripple a population that evolved in 0.3 g spin gravity. The atmosphere might be 30% oxygen, turning every spark into an inferno. Day length could be 72 hours, wrecking circadian rhythms that haven't seen a natural sunrise in 400 generations. Then there's the biochemistry we can't see from orbit. Alien microbes that treat human cells like a substrate. Pollen analogues that trigger anaphylaxis. Trace gases we never tested for because we didn't know they existed. Even the soil could be toxic, loaded with perchlorates or heavy metals that bioaccumulate. The ship's population spent 10,000 years adapting to an artificial environment. Now they have to readapt to a natural one they've never seen, that their biology may no longer tolerate, on a clock measured in weeks before supplies run out. Which is why the most dangerous moment of the entire 10,000-year voyage is the final landing. Deceleration burn. Deceleration takes longer than the entire journey so far. The ship has been coasting at 0.05 C for 10,000 years, engines dormant. Now those engines must fire continuously for 40 years to bring velocity down to orbital insertion speed, around 8 kilometers per second. The fuel for this burn was manufactured centuries ago. The magnetic containment systems holding the antimatter haven't been tested under load in millennia. If a single coil fails, the deceleration stops. The ship doesn't slow down. At 0.05 C, the target star system crosses your field of view in 3 days. There's no second chance, no orbit to salvage. You overshoot into interstellar space with no fuel left to correct. The crew will die of old age before reaching the next star, 12 light-years away. And even if deceleration succeeds, there's no guarantee the planet they're aiming for still exists. Planetary survey. The ship launches probes 6 months out. Radar maps the inner system, spectrometers sample atmospheric composition, gravimetric sensors check planetary mass. The data takes 18 hours to return at light speed. What it reveals could end everything. Earth's telescopes last observed this planet 10,000 years ago. In the time since, a near-Earth object could have impacted the surface, sterilizing the biosphere. A stellar flare could have stripped the atmosphere. Runaway greenhouse warming could have turned oceans into vapor and rock into lava. The ship's survey has 90 days to confirm habitability before resources run critical. Oxygen levels, radiation flux, tectonic stability, magnetic field strength. Any one parameter outside tolerance means the mission fails. After 10,000 years, the entire voyage reduces to a yes or no from a sensor package. And if the planet is gone, the ship has one final option, but it will divide the crew forever. The settlement split. The backup plan was written into the mission charter 10,000 years ago. If the primary target is uninhabitable, the crew votes, push on to the next candidate star 3,000 years away, establish permanent habitats on this system's moons and asteroids, or split. Splitting means dividing resources, population, genetic diversity. One group takes the ship and continues. The other stays, builds colonies on airless rocks, and adapts to low-gravity mining stations. Both groups lose redundancy. Both become more fragile. The vote is binding. Families separate. Couples divide. Cultural factions that coexisted under the unifying goal of reach the planet now fracture permanently. Some will never see sunlight. Others will never stop moving. But there's a deeper problem. After 10,000 years in space, can they even survive on a planetary surface anymore? Gravity shock. The ship's medical bay runs simulations on arrival day. Colony candidates step into the centrifuge at full planetary spin. Within 90 seconds, half of them collapse. 400 generations under 0.3 grams rotation have rewritten human physiology. Bone density drops 12% per decade without countermeasures. Cardiovascular systems pump blood through vessels that never had to fight a full gravity well. The first landing teams trained in the high-G modules for 20 years. They ran, lifted, broke bones and rebuilt them under load. But the elderly, the young, anyone born in the last 9,800 years of flight hasn't spent a single day above 0.4 grams. Surface gravity will fracture their hips, crush vertebrae, stop hearts that can't push blood uphill against 9.8 meters per second squared, which means the people who trained their entire lives for landing might be the only ones who can't walk on the surface. Atmospheric hazards. The air tests breathable. Oxygen at 19%, nitrogen at 78%, trace argon. The lander's hatch opens, and the first survey team steps out into an alien spring. Within 6 hours, 3 of them are dead. The planet's vegetation releases pollen analogues their immune systems have never encountered. Anaphylaxis hits faster than the epinephrine can. The remaining crew seals the hatch and waits. There are no bacteria in common between worlds, no shared evolutionary history, no reason Earth-origin antibodies should recognize anything here. But that cuts both ways. A benign soil fungus could colonize human lungs with zero resistance. A plant sap could be a contact neurotoxin. The ship carries 10,000 years of microbial passengers, gut flora, skin bacteria, fungal spores in the air ducts, mutations that evolved in the closed loop of recycled water and hydroponic nitrogen. And the planet's native life might not survive contact with them either. Contamination ethics. Exobiology detected chlorophyll analogues in 14 different species within 500 meters of the landing zone. Samples showed metabolic pathways Earth abandoned 2 billion years ago. This biosphere is not just alien, it's rare. The colony charter gives them 60 days to assess contamination risk, but the ship's microbes are already escaping. Every exhaled breath carries bacteria. Every footprint seeds the soil. Sterilization protocols assume you can contain a closed system, not 8,000 people who've been breathing recycled air for 400 generations. Earth's history offers a preview. Invasive species collapse ecosystems in decades. Rats on islands, fungi in forests, a single aggressive plant choking out everything that evolved without it. The colonists are the invasive species now. They traveled 10,000 years to reach a living world. If their presence ends it, the mission succeeded and failed in the same moment. Which forces the question, do they have the right to be there at all? The colony failure rate. History offers no comfort here. Of the English colonies established in the Americas before 1650, roughly 40% failed completely within 5 years. Roanoke vanished. Jamestown lost 80% of its settlers in the first winter. Biosphere 2, humanity's $200 million attempt at a sealed ecosystem in Arizona, collapsed in 21 months. Oxygen levels dropped to 14%. Crew health deteriorated. They had to open the airlocks. A generation ship colony faces every challenge Biosphere 2 did, plus gravity shock, unknown pathogens, and a biosphere humanity didn't design. First-year starvation is not a historical curiosity. It's a statistical likelihood. Even if the ship lands intact and the planet checks every box, the colony can still fracture. Resource allocation disputes, leadership succession crises, a single crop failure in year 2 with no supply chain to fall back on. And if the colony fails, there's no rescue. Earth is 10,000 years away and may not even know they arrived. Redundant missions, which is why every serious generation ship proposal includes redundancy. You don't send one ship, you send 3, or 5, or 10. Stagger the launches by decades. Aim for different star systems or different planets in the same system. If Ship A suffers a reactor failure 800 years in, Ship B is still en route. If Colony 1 collapses from disease, Colony 2 might thrive. The math is cold but correct. Independent missions, independent failure modes. But redundancy creates new problems. If 2 ships arrive at the same habitable moon within 50 years of each other, who controls the equatorial farmland? Do they merge populations or compete? And there's the ethical weight. You're not just risking one crew, you're knowingly sending thousands of people as backups, some of whom will die in transit so that others might succeed. Redundancy hedges the survival odds, but it multiplies the human cost. You're building a mission architecture that assumes failure, that plans for it, that budgets lives accordingly. But there's one design that sidesteps almost every problem we've covered, and it's the one solution nobody wants to talk about. The embryo alternative. It's called an embryo ship. No living crew, no multi-generational society, just frozen embryos, artificial wombs, and an AI caretaker system sophisticated enough to gestate, birth, and raise the first generation on arrival. The ship is smaller, lighter, faster. No life support for centuries of conscious humans. No social collapse, no mutiny, no genetic bottleneck from a living population of 500. You carry 10,000 embryos in a few cubic meters and let the machines do the rest. The first children wake up on a new world. They're raised by robots programmed with human culture, language, history. By age 20, they're colonists. By age 40, they're parents. The settlement begins fresh, unburdened by shipboard trauma or generation ship politics. It solves the biology, the sociology, the life support, the time. But it creates a question that might be even harder. Are they still us? Identity continuity. Think about what a child inherits without ever being taught. The lullaby a grandmother hummed. The way a whole town falls quiet on a certain night in December, the reason we flinch at some sounds and ache at others. None of that lives in DNA. It lives in the unbroken chain of people handing it down, and an embryo ship snaps that chain clean. The first generation wakes with no parents who remember Earth, no elders, no oral history, no one who watched a sunset over an ocean. Everything human that isn't genetic arrives as files in a database, a recording of a symphony instead of the room where it was first played, a photo of rain instead of the memory of standing in it. They'd be biologically identical to us and culturally untethered, building meaning from scratch on a world we'll never see, a colony maybe, or something closer to a new species wearing our genome. And if we accept that loss, there's an even more extreme solution that makes the generation ship obsolete entirely. Digital consciousness. What if you never sent bodies at all? What if you scanned a human mind down to every connection between its neurons, roughly 86 billion of them, and turned that pattern into pure information? Data doesn't need water, food, oxygen, or 10,000 years. Data travels at the speed of light. Beam that mind toward Proxima Centauri and it arrives in 4.24 years. On the far end, a machine reads the pattern and rebuilds it in a synthetic body already waiting there. No aging crew, no failing life support, no politics of the 20th generation. A person steps out onto an alien world barely older than when they left. Except one question refuses to go away. If the original you stayed behind and a perfect reconstruction wakes up 4 light-years away, which one is you? Maybe consciousness is just the pattern, and the pattern is all that matters. Or maybe you built a stranger who only thinks it's you. But whether we choose generation ships, embryos, or uploads, there's one thing none of these solutions can escape. The Fermi paradox. Here's what should keep you up at night. Every method we've explored is, in principle, possible. Difficult, expensive, morally fraught, but possible, with physics we already understand. So run the logic forward. The galaxy is 13 billion years old. A single civilization spreading even slowly could cross it in a few million years, a blink against that age. There have been billions of stars, billions of chances, all the time in the world. The galaxy should be humming with the signatures of others who left home. And yet we look, and we listen, and we find silence. Nothing on the radio, no probes, no lights where there shouldn't be lights. That silence has a name, and it points to a chilling idea called the Great Filter. Some barrier, somewhere, that stops life from making the leap we're contemplating. Maybe civilizations never survive long enough to try, or maybe they try, again and again, and the ships simply never arrive. And the unsettling possibility is that we're about to discover what that filter is. Existential risk. Consider the darkest reading of the numbers. Not that a single ship fails, but that no ship can ever succeed, because the physics we're betting on doesn't cooperate. Deep space isn't the mild vacuum we model from low Earth orbit. Beyond the sun's protective bubble, galactic cosmic rays hit harder and more often than any shielding we've tested against. If the true radiation background is even a few times higher than our probes have measured, every cell on board accumulates damage no lead wall can fully stop. And there's a quieter failure mode that has nothing to do with radiation at all. We have zero data on whether humans can stay sane and cooperative, sealed in a metal shell, for 300 generations. Maybe confinement on that scale always ends in collapse, the way isolated communities on Earth fracture in decades, not millennia. If any one of these is a hard limit rather than an engineering problem, the whole idea dissolves, which would mean humanity is permanently locked to Earth, and every generation ship is just a slower way to die. The breakthrough wait. So maybe the answer isn't to launch at all. Maybe it's to wait. A ship that crawls at a fraction of light speed needs 10,000 years to reach a nearby star. But fusion propulsion, if we ever tame it, could cut that to a few centuries. Antimatter, gram for gram, packs the most energy any fuel could theoretically hold, and even speculative warp-adjacent physics keeps flickering at the edges of serious research. Push the cruise speed high enough, and the 10,000-year odyssey shrinks to a single human lifetime. No generations born and dying in transit. No 300-link chain where one broken link ends everyone. Launch too early, and you condemn thousands of people to a voyage that a later ship, faster and safer, could overtake and beat to the destination. You'd have spent the crew's entire existence on a trip that was obsolete before it finished. But waiting assumes civilization survives long enough to develop that technology, and that's not guaranteed. Civilization fragility. Because Earth is not a stable platform to bet forever on. A warming climate that pushes past tipping points. A nuclear exchange that darkens the sky for years. A single asteroid, the kind that ended the dinosaurs 66 million years ago, arriving with no warning we managed to catch in time. Add engineered pandemics and artificial intelligence that pursues goals no one intended, and the list of ways this one planet could go quiet keeps growing. Every one of those threats shares a feature. They all hit Earth, and only Earth. A ship already underway when the worst happens carries the only humans left who aren't in the blast radius. Suddenly, the slow, wasteful, 10,000-year crawl isn't a luxury we can postpone. It's the single copy of us that survives the fire, which makes the generation ship less a colonization mission and more a lifeboat, and lifeboats don't wait for better weather. Current proposals. So where are we actually building one? Breakthrough Starshot aims to send tiny light sail probes to Alpha Centauri at 20% light speed, but those carry cameras, not people. NASA's Project Hyperion ran a design study in 2023 for a multi-generational ark capable of reaching nearby stars in 250 years, complete with rotating habitats and closed-loop life support. Icarus Interstellar has drafted blueprints for fusion-driven ships housing 10,000 to 50,000 passengers, with agricultural decks stacked 12 levels deep. None of them have funding. None of them have a construction timeline. Hyperion's study cost $500,000 and produced a 300-page report that sits in a database. Icarus Interstellar operates on donations. Breakthrough Starshot has $100 million, but it's aimed at postage stamp probes, not arc ships weighing millions of tons. The designs exist, the physics checks out, the materials are available or within reach. But not one government, not one coalition, not one private investor has committed the trillions required to actually start. Because the hardest part of building a generation ship isn't the engineering, it's convincing anyone to actually do it. The motivation problem. A conservative estimate puts a single generation ship at $10 million to $50 million spread across 50 to 100 years of construction. That's multiple Apollo programs running in parallel for half a century, with no tangible return until people who haven't been born yet reach a planet none of us will ever see. Democratic governments work in 4 or 5-year election cycles. Corporate boards answer to quarterly earnings. Even if a coalition formed, who leads it? The country that funds 40% of the ship doesn't control the destination. The corporation that builds the reactor doesn't own the arrival. You'd need binding treaties that survive regime changes, economic collapses, wars. The International Space Station cost $150 million and required 15 nations to barely hold together for 25 years. A generation ship requires 100 years of cooperation with no photo ops, no ribbon cuttings, no visible milestones until the hull is already in orbit. The incentive structure is backwards. The sacrifice is ours. The benefit belongs to people 300 years downstream. And even if the money and political will existed, there's one final question nobody's answered. Who decides who goes? Selection ethics. You need at least 500 genetically diverse individuals to avoid inbreeding collapse. Ideally, 10,000 to sustain a stable population. Those people need to span age groups, skill sets, personality types, and genetic profiles that maximize adaptation to an unknown world. Do you select by merit, by lottery, by national quota? If China has 18% of Earth's population, does it get 18% of the seats? Does Luxembourg get one? A pure lottery feels fair until you realize it could fill the ship with people who lack critical skills or share genetic vulnerabilities. A pure meritocracy means the wealthy and educated dominate selection, leaving the global poor behind. A national quota system turns the ship into a political battleground where every seat is leverage, and whoever makes the final call has just decided which branch of humanity survives and which stays behind to face whatever's coming. There's no precedent for this. Refugee resettlement, immigration policy, disaster evacuations all operate under existing power structures. A generation ship is a blank slate, and every selection framework carries an ideology. The criteria you choose encode a vision of what humanity should be, which means you're not just picking passengers, you're editing the species. But all of this assumes we're asking the right question, and we might not be. The core question, because here's what we've been circling around. The question was never whether a generation ship could keep humanity alive for 10,000 years. The question is whether the people who step off at the end are still human in any way that matters to us. After 400 generations sealed inside a metal cylinder, they won't just speak differently or worship different gods. Their bones will be lighter, their eyes adjusted to artificial light, their immune systems shaped by a closed ecosystem with maybe 2,000 unique microbial strains instead of Earth's trillions. They'll carry mutations we can't predict, selected not by survival on a planetary surface, but by survival in a corridor. Their concept of sky, of weather, of solid ground under open air will be academic, legends their parents stopped believing. You're not preserving humanity, you're launching a 10,000-year experiment in what humanity becomes when you change every environmental pressure that made us. And whether that's a success or a failure depends entirely on what we think humanity means. The answer. So here's the answer. Yes, a generation ship could biologically keep humans alive for 10,000 years. With perfect closed-loop life support, radiation shielding, a genome management program, rigid social structures to prevent collapse, and an unbroken chain of technological knowledge, the species survives. But the humans who arrive won't be the humans who left. They'll be adapted to microgravity or spin gravity, to recycled air and artificial seasons, to a world where the word outside means a hallway, not a planet. Their culture will have drifted through 400 generations of oral tradition, power struggles, and isolation. Their DNA will carry the fingerprints of genetic bottlenecks and selection pressures we can't foresee. The ship doesn't preserve humanity, it transforms it. What walks off at Proxima Centauri b is something new, shaped by the longest unbroken voyage in history, a branch of the family tree that took a different path. And if that's what we're willing to call success, then yes, it could work. The departure. Picture the first generation as Earth falls away behind them. They're the only ones who'll remember weather, the smell of rain on soil, the feeling of wind that isn't recycled through a ventilation grid. They're the last to have stood on ground that wasn't a floor. For the first 18 months, they'll still receive messages from home, news, updates, faces of people they left behind. Then light-speed delay makes conversation impossible, and the transmissions become recordings, ghosts talking into the dark. By year 5, Earth is a blue pixel. By year 20, it's lost in the glare of the sun. They'll hold memorial services for people who died 7 light-years behind them, and the grief will arrive years late. The mission becomes irreversible, not when the engines fire, but when the last person who remembers Earth as more than a story dies. That first generation signed up for it. They knew the deal, made peace with it, believed in the mission enough to go. But what nobody prepared them for was what happens when the first child is born who will never see a horizon. The generations between. By generation 50, nobody remembers Earth as anything but a myth passed down in school. The adults teach navigation algorithms they've never used. They drill landing protocols for a world they'll never see. They maintain systems for people who aren't born yet. The radiation shielding starts showing microfractures in year 3200. A mutiny attempt in generation 87 gets suppressed, but the social cohesion never fully recovers. By year 6000, the genetic diversity bottleneck becomes measurable in birth defects. The closed-loop agriculture begins accumulating trace toxins no one anticipated. Every single one of those 58 problems compounds. The middle generations inherit them all at once, layered, interacting, cascading. They're not pioneers and they're not colonists, they're maintenance. And then, 10,000 years later, the ship arrives. Arrival day. The first thing they'd see through the viewports is a star they've studied their entire lives, now close enough to cast real light through the corridors. The second thing is a planet, not a photograph, not a simulation, an actual world. But here's what nobody can predict. Whether bones grown in 0.3 G can handle 1.0 G without fracturing. Whether immune systems, shaped by 400 generations in sterile recycled air, can survive a biosphere's microbial reality. Whether minds conditioned by metal walls and artificial horizons can psychologically process an open sky. They'd be human, technically. Same DNA, mostly, but shaped by selection pressures Earth never imposed. They'd speak a language drifted beyond recognition. They'd carry cultural knowledge from a homeworld that existed 10,000 years ago. The promise was survival. The question is whether what arrives still counts. Which brings us back to the question we started with. The verdict. Could a generation ship keep humanity alive for 10,000 years? The technical answer is, not with anything we can build today. No single design solves all 58 problems at once. The radiation shielding that works adds too much mass. The closed ecosystem that's stable enough requires a scale we can't launch. The social structure that prevents collapse contradicts the genetic diversity we'd need. But here's what matters. Every one of those problems has a theoretical solution. Radiation shielding works if you can manufacture it in space from asteroid material. Ecosystems stabilize at sufficient scale. Genetic diversity holds if you bring frozen embryos and artificial wombs. Social cohesion becomes possible with the right governance algorithms and cultural design. None of it violates physics. The limits are engineering, resources, and will. We can't build it in 2026. We might be able to build it in 2150. The question isn't whether it's possible. The question is whether it's worth it. But there's one thing we haven't talked about yet. Why we ask. Why do we ask whether a generation ship could work? Not because we're about to build one. We ask because the question forces us to examine every assumption we make about survival, about systems, cycles, inheritance. A generation ship is a test of resilience stretched across centuries. It shows us how fragile our oxygen is, how thin our social contracts are, how easily knowledge disappears between one generation and the next. We've walked through 400 years of radiation, mutation, language drift, gravity failure, phosphorus depletion, mutiny, speciation, and atmospheric shock. The mission is nearly impossible. And yet the need for it grows every year we remain on one planet. As of 2026, no generation ship is funded, no hull is being welded, but the physics papers keep coming, the life support models keep improving, the question keeps sharpening. This story isn't over, not even close. If you want more deep dives into the cosmos and the questions that define it, subscribe. There's a lot more universe to walk through.